Good day, what's on the menu today? A monotonic divergent series of odd numbers. The sum from n equal 1 to infinity of 2n minus 1, which are the odd numbers 1 plus 3 plus 5 plus 7 plus 9, etc., is equal to 1/3. We're going to go through 8 proofs in this video. Proof number 1, generating function. So when you work with a divergent series of integers, always start with the generating function. If you know it, it will, when you evaluate it at the value of x, generating the divergent series of integers that you're looking at, it will give you directly the value of the sum of the divergent series of integers that you're dealing with. So let g of x be the ordinary generating function for the monotonic divergent series of odd numbers. So the expression of the ordinary generating function gf of x is equal to 1 plus x over 1 minus x squared. So that is a closed form, and in expanded form it is of course 1 plus 3x plus 5x squared plus 7x to the cube plus 9x to the fourth, etc., which you can see by replacing x with 1, it will give us the divergent series of odd numbers. So let's evaluate the above function with x equal 1, and then we obtain the generating function at x equal 1, 1 plus 3 plus 5 plus 7 plus 9 plus 11, you can see it. Now if we replace x equal 1 in a closed form, 1 plus x over 1 minus x squared, we obtain, of course, 2 over 0 squared, which is 2 over 0, which is infinity. So applying the fundamental theorem of divergent series of integers, we conclude that the monotonic divergent series of odd numbers is unstable. Why unstable? Because when you evaluate its generating function at the value of x, generating that divergent series or monotonic divergent series of odd numbers, the value of the ordinary generating function is not finite, it's infinite. Therefore, it is the series, divergent series of odd numbers, monotonic one, is unstable. Therefore, we cannot determine the sum of the divergent series by evaluating its ordinary generating function with the value generating the series at x equal 1. Therefore, proof number 1 is not a proof. It's not working. Proof number 2, direct calculation. So in that proof, we will establish the sum of the monotonic divergent series of odd numbers as being the sum of two other monotonic divergent series, well-known divergent series. So let's write it down. The divergent series, monotonic divergent series of natural number 1 plus 2 plus 3 plus 4 plus 5 plus 6 is equal to, let's open the toolbox, the sum from n equal 1 to infinity of n, which is basically the sum of the natural number, is equal to negative 1 over 12. Let's plug it in. Plus the other one, which is the sum of the natural number starting from 0, which is the sum of the whole number, 0 plus 1 plus 2 plus 3 plus 4 plus 5, etc. Open the toolbox. The sigma of from n equals 0 to infinity of n is equal to 512. Let's plug it in. Remember that divergent series, that monotonic divergent series of natural number is unstable. Therefore, by inserting a leading 0 leads to a separate different sum. Now let's sum those two monotonic divergent series. It will give us the monotonic divergent series of odd numbers. Remember, column by column, 1 plus 0 equal 1, 2 plus 1 is equal to 3, 3 plus 2 is equal to 5, 4 plus 3 is equal to 7, etc. 5 plus 4 is equal to 9, 6 plus 5 is equal to 11. And then we do the same on the right-hand side. The sum of the sum will be the sum of the divergent series, monotonic divergent series of odd numbers. So negative 112 plus 512 is equal to 1/3. It's equal to 4 over 12, which is 1/3. So in sigma notation, if we write the above in sigma notation, we have the sum from n equal 1 to infinity of 2n minus 1 is equal to the sum from n equal 1 of n plus the sum of n equals 0 to infinity of n. In other words, the sum of the natural number starting from 1 plus the sum of all numbers starting from 0. The first one is negative 112. We can plug it in here. The second one is plus positive 5 over 12. Plug it here. And we have, of course, 5 minus 1, 4 over 12, which is, of course, 1/3. And that is the correct result. So in terms of understanding that looking at the generating function, ordinary generating function, of course we can decompose 1 plus x over 1 minus x square as the sum of 1 over 1 minus x square plus x over 1 minus x square. So that's exactly the same thing as here. What we have there is a monotonic divergent series of natural numbers starting from 1 here, and here the same thing shifted, single shifted by 1 to the right. In other words, that ordinary generating function corresponds to the divergent series of natural number, or monotonic divergent series of natural number, and here it's the same thing with a single shift. You can see the single shift x being represented with a 0 here of the natural number 1 plus 3 plus 1 plus 2 plus 3 plus 4 plus 5, etc. So that sum that we have here, the plus and the equal sign here, correspond to the plus and the equal sign there, with the x representing the single shift in front. Exactly the same thing. So when you understand and you're able to read those ordinary generating functions like that, not to decompose it algebraically, but to do the interpretation in terms of divergent series, then you're halfway there to understand the divergent series and how it works. Okay. Let's have a look at another direct calculation. So another example of direct calculation using the sigma notation is as follows. The sum from n equal 1 to infinity of the odd numbers to n minus 1, because we start numbering from n equal 1, is equal to 2 times the sum of n equal 1 to infinity of n minus the sum from n equal 1 to infinity of the constant 1. So let's open a toolbox. What is the sum of n equal 1 to infinity of n, which is nothing else than the sum of the natural number? It is equal to negative 1 over 12. And what is the sum from n equal 1 to infinity of the constant 1, which is 1 plus 1 plus 1 plus 1 forever, is equal to negative 1/2. So we can plug those values into the equation here. Negative 112 for the first sigma, negative 1/2 for the second sigma, and it gives us negative 112 times 2, so which is of course negative 1/6, minus negative 1/2, which is plus 1/2, and then plus 1/2 minus 1 over 6 is equal to 1/3. So that gives us one line, the correct sum of the monotonic divergent series of odd numbers. Proof number 4, intercept function. So we need a bigger whiteboard for this one. Let's go step by step. Step number 1, calculate the partial sum of the monotonic divergent series of odd numbers. So the monotonic divergent series of odd number 1 plus 3 plus 5 plus 7 plus 9 plus 7, etc. The partial sum, the first term of the sequence of partial sum, will be equal to the first term of the divergent series, which is 1. Then 1 plus 3 equals 4, 4 plus 5 equals 9, 9 plus 7 equals 16, 16 plus 9 equals 25, 25 plus 11 equals 36, etc. So we recognize now the sequence of partial sum being the squares. So once we have identified that, we can express the partial sum S of n, uppercase n, being the index for the sequence of partial sum, as a closed form expression, S of n, which is the sum from lowercase n equal 1 to uppercase n of 2n minus 1, is equal to, let's open the toolbox, the sum from n equal 1 to n of 2n minus 1 is equal to n squared. We can see it here. So here is the n squared. Then step 3a, we calculate the intercept point, h of n, uppercase n, h for intercept, as a half sum of the two consecutive partial sum. So h of n is the arithmetic average of the partial sum at n minus 1 plus the partial sum at n. So the partial sum at 1/2 of the partial sum at n minus 1 is of course n minus 1 square over 2 plus the half of the partial sum at n, which is n squared over 2. If we simplify that, we have n times n minus 1 plus 1/2. Assuming s at 0 equals 0. In other words, we make an assumption that before we start here, it's 0 and there's nothing, so we start at 0. That's the assumption that we need here for the value of n equal 1. S0 is here. So step 3b, we express the continuous intercept function h of x simply by replacing the discrete variable uppercase n that we use for the sequence of partial sum with the continuous variable x. So again, h of n equal n times n minus 1 plus 1/2. We just plug in the value of x. h of x is equal to x times x minus 1 plus 1/2. So we ran out of space on the board, so let's scroll up the other board. So let's carry on. Step number 4, let's evaluate the continuous intercept h of x, where x equals 0. So the function, we have seen it on a previous board, when we evaluate at x equals 0, h of 0 is equal to 1/2. Therefore, the sum from n equal 1 to infinity of 2n minus 1, which is the monotonic divergent series of odd numbers, 1 plus 3 plus 5 plus 7 plus 9, etc., is equal to the value of the intercept at x equals 0, which is the intersect of the intercept with the vertical axis after projection of q. Given that 1/2 is already a rational number, it's equal to 1/2. Is that the correct result? Nope, it's not the correct answer. So unfortunately, we have to carry on with step 5a, which is to use the adjusted intercept for the monotonic divergent series of odd number, which is a parabolic function h sub a of x expressed as h sub a of x, x times x minus 1 plus 1/3. That's where the adjustment is. Now when we do the same thing as previously, we have a step 5b to evaluate the value of the intercept, adjusted intercept, h sub a at x, where x equals 0. It gives us, of course, 1/3. And then, finally, we have the sum from n equal 1 to infinity of 2n minus 1, which is 1 plus 3 plus 5 plus 7, etc. The monotonic divergence of odd numbers is equal to the value of the adjusted intercept at 0, evaluated at 0, or the intersect of the adjusted intercept intersecting with the vertical axis after projection on q, which is 1/3, and that is the correct result. So that method that we use is correct. Unfortunately, that proof number 4 does not qualify as a proof. Why? Even though it's correct, the method is correct, because here we haven't proven the 1/3. We just brought it here. There is a method that we can use, which is a PSI integral for the case-shifted monotonic divergence of series of integers. We will treat that on a separate video, so we haven't proved it here, but the proof is correct, except here we haven't justified the 1/3 there. Okay. Proof number 5, partial sum integral, also known as PSI method. So, step number 1, let's calculate the partial sums. We have seen it on the previous slide, 1 plus 3 plus 5 plus 7 plus 9, etc. The partial sums, or the sequence of partial sums, is the sequence of square numbers, 1, 4, 9, 16, 25, etc. So step 2a, let's express the partial sum S of n as a closed form expression. So it's easy. S of n is the sum from lowercase n equal 1 to uppercase n of 2n minus 1. We can quickly open the toolbox, but we have seen it on the previous slide. It's n square, and we can see it here, so we can plug n square here. N being a discrete variable, a natural number. And step 2b, we express the continuous partial sum S of x, x being now a real number. So S of n equal n square, we just plug in x. X being a real variable. Step number 3, we calculate the PSI. So the PSI, by definition, is the integral from -1 to 0 of the continuous partial sum S of x dx. So in that case, it becomes the integral from -1 to 0 of x squared dx. So we need the antiderivative here. So the antiderivative of the indefinite integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus a constant. But because we have bound of integration here, -1 and 0, the constant will cancel itself out. So we will only bother about the x to the n plus 1 over n plus 1, which is equal, in that case, x cubed over 3, integrated from -1 to 0. So for 0, it's 0 minus -1 to the cube divided by 3. So the negative sign will cancel each other out, and we're left with 1/3. So we can finally write down that the sum from n equal 1 to infinity of 2n minus 1, which is the monotonic divergent series of odd numbers, is equal to the PSI value here after projection on Q, because 1/3 is already a rational, we don't have to project, but generally speaking, remember that you need to project on Q for divergent series of integers, and it's equal to 1/3, which is a correct result. So we can interpret that value as the area under the curve. You can see the parabole here, given by the equation x squared. So the area under the parabole, under the curve, between -1 and 0, which is a blue, light blue shaded area here, is equal to 1/3, and that area corresponds to the sum of the divergent series of odd numbers. Proof number 6, Ramanujan summation. So let us apply Ramanujan's summation method. What is Ramanujan's summation method? So the sum from n equal 1 to infinity of the function f evaluated at n is equal to -1/2 of the function evaluated at 0 minus the sum from m equal 1 to infinity of the even Bernoulli number divided by 2m factorial times the 2m minus 1 derivative of that function f evaluated at 0. So again, where the b sub 2m is the 2m's Bernoulli number, actually the 2m's plus 1 Bernoulli number, because we start numbering the Bernoulli numbers at b0 equal 1. So it's actually the 2m plus 1 Bernoulli number in a context of b1 equal plus 1/2. So when you work with the Bernoulli numbers, always specify the context. You have two contexts possible, b1 equal plus 1/2 and b1 equal -1/2. So always specify which context you're working in. In that case, b1 equal plus 1/2. So using f of n equal 2n minus 1 for any n greater or equal than 0. So f of n equal 2n minus 1, evaluated at 0, obviously it's -1. The first derivative of f at n, minus 1 is a constant, it's gone, we're left with 2n, derivative is 2. Evaluated at 0 remains 2, it's a constant. The second derivative of n, derivative of a constant here, it becomes 0, and then of course evaluated at 0 remains 0, and that stays the same afterwards. The 2m minus 1 derivative of f evaluated at n is constant 0, therefore evaluated at 0 is 0. So, and that is true for any integer value m greater or equal to 2. So when we plug those results into the equation Ramanujan's summation method above, we have the sum from n equal 1 to infinity of f of n is equal to, of course, the sum of n equal 1 to infinity of 2n minus 1. That's how we define the function f, because we are dealing with a monotonic divergence of odd numbers. So the sum of 2n minus 1, which is equal to -1/2 of f of 0, minus b sub 2 over 2 factorial of the first derivative of f at 0, evaluated at 0. And the reason for that is because all the other derivative of f, or the odd derivative of f, are all equal to 0. So we're left with this. So when we evaluate the first half, f0 is -1, so over 2 is -1/2. F prime at 0 is equal to 2. So we can regroup here. We have 1/2 minus 2 times Bernoulli sub 2, b2 over 2 factorial. So obviously 2 factorial is equal to 2, so it's simplified here. We are left with 1/2 minus b2. So let's open the toolbox. What is b2? So we know we are in a context here of b1 equal plus 1/2, but that is not what we are after. We are after the value of b2, which is 1/6. So we plug 1/6 here. It gives us 1/2 minus 1/6, which is of course 3 minus 1/6, 2/6, which is of course 1/3. And that is the correct result. So the Ramanujan summation takes us to the correct result, 1/3, which is the sum of the monotonic divergent series of odd numbers. Proof number 7, Abel-Plana summation. So Abel and Plana are two mathematicians from the first half of the 19th century who came up with that summation method independently a few years apart. So let us apply Abel-Plana's summation method for monotonic divergent series, and can be expressed as follows. So the sum of n equal 1 to infinity of f of n, it starts like Ramanujan summation method, -1/2 of f evaluated at 0. But then it's different, it's plus I, the sum, the integral, from 0 to plus infinity of that function evaluated at it minus that function evaluated as negative it over e to the 2 pi t negative 1. So there's two formulas. There are two formulas for the Abel-Plana summation, one for the monotonic divergent series, where the denominator is e to the 2 pi t minus 1, and one for the alternate divergent series, where the denominator will be a hyperbolic sign. So make sure you use the correct function depending on your divergent series being monotonic or alternate. So using f of x, s being a complex number notation, so 2s minus 1, of course we're dealing with odd numbers. F at 0 is equal to negative 1, that's obvious. F of it, 2it minus 1, and f evaluated at negative it becomes negative it minus 1, so minus bracket 2it plus 1. So plugging in the integral, we obtain the sum from n equal 1 to infinity of 2n minus 1, which is our monotonic divergent series of odd numbers, is equal to negative 1/2 of f0, f0 being negative minus 1, so it becomes 1/2 plus I of 4it over e to the 2 pi t minus 1, dt, t being our integral for the variable for the integral. So how can we rewrite that? So let's split the 4 into 2 times 2. I keep a 2 here and I put another 2 inside the derivative here. And I'm introducing a pi there as well, 2 pi t, and then also 2 pi t in that case there. So I've introduced pi square, that's why I divide in front of the integral by 1 over pi square to balance it out. So you can see, you take that pi and this one, simplify with this one, and 2 times 2 equals 4, you left with 4it. The I came in front, I square become negative sign. So if you work it backwards, you can see you landed up into here as well. So what's the reason of writing it like this as a 2 pi t as a variable? Because we will be able to use the Bose integral, which is defined as the integral from 0 to plus infinity of, in a u world, u to the s minus 1 over e to the u minus 1. So now if we replace the u by that variable that we have 2 pi t, we can see integral from 0 to plus infinity of 2 pi t to the s minus 1 over e to the 2 pi t minus 1 d of 2 pi t. And then of course the bound of integration do not change. When t equals 0, 2 pi t is also equal to 0, u, and same with infinity. When t equals infinity, infinity times 2 pi is also equal to plus infinity. So that does not change. So here, that's where we use that Bose integral. The result is that integral is equal to gamma of s, the gamma function evaluated at s, times the Riemann zeta function evaluated at s. That gives us that integral. So we can use that result for s equal 2. So we bring in front the negative 1/2 minus 1 over pi square. And that integral, if you look for s equal to, s minus 1 is of course equal to 1. So that value for 1 at the exponent is equal to what we have here. Therefore, it is equal, the value of that expression is equal to 1/2 minus 1 over pi square of gamma evaluated at 2 times Riemann zeta function evaluated at 2. So let's open the toolbox. Gamma of 2 is equal to 1 factorial. Remember, gamma of n is not equal to n factorial. It's equal to n minus 1 factorial. And then, of course, 1 factorial is equal to 1. And the Riemann zeta function at 2 is equal to pi square over 6, which is the Basen's problem. So I call that one the Basel constant, pi square over 6, that Euler resolved in the mid-18th century. So let's plug in those values. Gamma of 2, 1 factorial equal to 1. Zeta at 2, pi square over 6. So of course the pi square will simplify each other, and we are left with 1/2 minus 1 over 6. 1/2 minus 1 over 6, of course it's equal to 1/3, and that is the correct result for the monotonic divergent series of odd numbers. That is the sum. Proof number 8, Hurwitz zeta function. So what is the Hurwitz zeta function? Zeta of s comma p over q, p and q being two integers coprime cube different of 0, of course, is defined as zeta s comma p over q. It's the sum from n equals 0, not 1, 0 to infinity of 1 over n plus p over q to the s. So S being a complex variable. So the sum of the monotonic divergent series of odd number is not equal to, but corresponds to the Hurwitz zeta function evaluated with S equal -1, P equal 1, Q equal 2. In other words, S equal -1, P over Q equal 1/2. So let's write it down. Zeta -1, 1/2 is equal to the sum from n equals 0 to infinity of 1 over n plus 1/2 to the -1. Because the exponent is negative and we are the denominator, we can pass that thing at the numerator. So it's equal to the sum from n equals 0 to infinity of n plus 1/2, which can be rewritten by factoring 1/2 in front as 1/2 of the sum from n equals 0 to infinity of 2n plus 1. So what is that value of the Hurwitz zeta function evaluated as -1, 1/2? Let's open the toolbox. And the value of that Hurwitz zeta function, -1, 1/2, is equal to 1/6. So we plug it here. Now we can write that the sum from n equals 1 to infinity of 2n minus 1 is equal to the sum from n equals 0 to infinity of 2n plus 1. You translate the index by +1 here. Inside the bracket, therefore, you decrease by -1 inside the sum, the discrete sum here. And that value, you just take the 1/2, pass it in front, is equal to 2 times the Hurwitz zeta function at -1, 1/2. Therefore, 2 times 1/6, therefore 1/3. And that's the correct value that we were after. So what have we learned today? We learned that the sum of the monotonic divergent series of odd numbers, 1 plus 3 plus 5 plus 7, etc., is equal to 1/3. We went through 8 proofs. 6 were valid and complete. 1 proof was valid but incomplete. We did not justify that adjustment of 1/3 into the adjusted intercept. And 1 proof didn't work due to the instability of this monotonic divergent series of odd numbers. So thank you very much for watching.